In the last lecture, I have introduced a sequential procedure for testing of hypothesis, and in fact, we have considered the simplest possible situation, that is the simple hypothesis versus simple hypothesis problem, for which most powerful test is available using Neyman Pearson lemma when the sample size is fixed. However, we have proposed a procedure which is sequential in nature. That means, at each stage we may take a decision to accept the hypothesis, to reject the hypothesis, or to continue further. When another observation is taken, then again the same decision criteria is, and the criteria to accept or reject or to continue is adopted. We proved certain important properties in general. Now, we will prove it for the proposed procedure, and we will also look at certain other characteristics of this sequential probability ratio test as proposed by Abraham Wald. Firstly, we give a lemma. We first give a general result which will be useful later. If y is a random variable, taking values 0, 1, 2 and so on, then expectation of y is equal to sigma probability of y greater than or equal to k, k is equal to 1 to infinity. So, expectation of y is sigma k into probability y is equal to k, k is equal to 1 to infinity. Actually, it is k is equal to 0 to infinity, because 0 value is also allowed here. However, this will not play a role. So, we can express it like this. This is sigma k equal to 1 to infinity, k times probability y is equal to k, because corresponding to 0 the term vanishes. Now, this term we expand. So, this is actually probability of y is equal to 1 plus probability of twice probability y is equal to 2 plus thrice probability y is equal to 3 and so on. Now, we express it like this. So, probability y is equal to 1, that is the term here. Then probability of y is equal to 2, one term is coming here and another term is coming here, which I write in the next row. Now, probability y is equal to 3, this is coming 3 times. So, I write in this 2 rows like this, and then we add one more row here like that. Now, you notice here the nature of the rows. In the first row, all the terms are coming from 1, 2 and so on. In the second term, probability y is equal to 1 is missing, it is starting from 2 onwards. In the third row, 1 and 2 are missing, it is starting from 3 onwards. So, this is nothing but actually probability of y greater than or equal to k for k equal to 1 to infinity. So, this proves this lemma. This lemma will be useful in certain results to be proved later. Let us look at the following result. We call it theorem 4. So, I am considering the previous numbers which I gave in the lecture 37, theorems 1, 2 and 3 etcetera. So, let x 1, x 2 and so on be a sequence of independent and identically distributed random variables, and a sequential procedure with a given stopping rule be defined. Suppose after n steps, the procedure gives a decision and z x is any measurable function, then expectation of modulus z x exists and expectation of n exists. Then this implies that expectation of S n is equal to expectation of z into expectation of n, where actually this S n is the sum, as I had defined earlier, of the first n terms. Only thing is here n is random. Okay. That is n, this n is random here. That is why we are talking about expectations, etc. So, this is S n is actually a random sum of random variables, because how many terms are there, that is random here. To prove this, so this is a very useful result, because you are writing expectation of S n as product of expectation z and expectation n here. Let us denote a quantity called y I. It is 1 if no decision has been taken up to stage I minus 1. Then it is 0, and it is 0 if a decision has been taken up to stage I minus 1. So, this y I is actually indicator that the decision has not yet been taken up to the previous stage, that is I minus 1th stage. Okay. So, now the decision making process up to at a particular level m, it depends upon the random variables x 1, x 2, x m. So, when I say the decision has not been taken up to stage I minus 1 or a decision has been taken up to the stage I minus 1, that means the random variables which are involved in this discussion, they will be x 1, x 2, x I minus 1. That means, this y I is directly a function of x 1, x 2, x I minus 1 alone. That means, it is actually independent of x I. Okay. So, if it is independent of x I, then it is independent of z x I, that is z I also. So, from this definition, we can say that y I is a function of x 1, x 2 and so on, x I minus 1, and so y I and z of x I, they are independent. Now, let us consider S n. So, S n is actually sigma of z x I from 1 to n, but what is the meaning of this n? That means, the decision is taken at the stage n. So, if the decision is taken at the stage n, then that particular y I will be 0. So, we can express this as simply y I z of x I is equal to 1 to infinity. because whenever the decision is taken at that stage, this will become 0 and up to that stage you will be counting. So, for example, if the decision is taken at the stage stage 1, then this will be 0. If the decision is taken at the stage 2, then y 1 will that is the first one will come, that is z 1 will come, and so on. Then z 1 plus z 2, z 1 plus z 2 plus z 3 and so on will occur. So, now we can write expectation of S n, that is equal to sigma I is equal to 1 to infinity expectation of y I z of x I, and I have said that y I and x I are independent. So, this becomes sigma expectation of y I into expectation of z of x I is equal to 1 to infinity. Okay, as y I and z x I are independent. Now, this x i's are I I d. So, I can write one of them. So, this is actually becoming expectation of say z x 1 and sigma expectation of y I is equal to 1 to infinity. That is equal to expectation of z x 1 into, now this term you can write as probability of n greater than or equal to I, sigma I is equal to 1 to infinity. Why? Because this value will be 1 till the stage the decision is not taken, after that this will become 0. So, it means if up to the ith stage the decision has not been taken, that means n is greater than or equal to I. Now, we can use the lemma which I just now stated, that is, if I am having a integer valued random variable of this nature, then probability y greater than or equal to k is nothing but the expectation. So, this quantity becomes nothing but expectation of n. So, we can write it as expectation of z into expectation of n using lemma 1. Because this expectation of y I is actually 1 into probability n greater than or equal to I plus 0 into probability of n less than I. So, that is why this quantity is actually equal. Now, so this proves actually this theorem here, that expectation of S n is expectation z into expectation n. Now, in order to check, or you can say prove, that the Waltz sequential probability ratio test terminates with probability 1 under both H naught and H 1, we will apply theorem 3. In the theorem 3, we have said that probability that modulus z x should be greater than 0 is greater than 0. This probability should be positive. That means, we should prove that both under H naught and H 1 probability of modulus z I should be positive. So, we need to prove that probability of modulus z I greater than 0 is greater than 0 under both H naught and H 1. Now, let us recollect the definition of z, that is ln of f 1 x by f naught x. Okay. So, if we consider expectation of z less than 0, then this will imply that probability of z is less than 0. This 0 denotes this is under H naught, this is greater than 0, which will imply that probability of modulus z greater than 0 is greater than 0. Similarly, if I consider expectation of z under H 1 to be positive, then certainly this will imply that probability of z greater than 0 under H 1 must be positive. That means, probability of modulus z greater than 0 is greater than 0. That means, these are two sufficient conditions for these statements. So, we must prove that expectation of z is less than 0 and expectation of z under 1 is greater than 0. Now, let us look at these quantities. What is expectation of z under H naught? That is equal to expectation of log of f 1 x by f naught x. Now, we use Jensen's inequality. What is Jensen's inequality? That is, if g is a convex function and x is a random variable with certainly expectation x finite and expectation of g x finite, then g of expectation x is less than or equal to expectation of g x. Okay. Now, if we want to use this, you observe that minus log of, let me write g x is equal to minus log of x. Then this is convex, because if I differentiate, I will get minus 1 by x, second differentiation will be 1 by x square. Let us take, say, x is positive. Okay. In that case, what is happening is that this quantity will be less than log of expectation f 1 x by f naught x, because with a minus log this will be greater than. So, if I take minus minus from both the sides, I will get less than. Now, this quantity, let me expectation of f 1 x by f naught x under H naught, that is equal to integral f 1 x by f naught x into f naught x d mu. Now, this cancels out. So, you get 1. So, this log of this actually becomes 0. So, expectation of z under H naught is less than 0. Similarly, let us consider, say, E 1 z. Now, E 1 z is equal to E 1 of log of f 1 by f naught, which we can write as minus E 1 log of f naught by f 1. Now, minus log is convex. So, this is greater than minus log of expectation f naught by f 1 under H 1. Once again, expectation of f naught by f 1 under H 1, that is equal to integral f naught by f 1 into f 1 d mu. So, this cancels out, this is equal to 1. So, this is actually equal to 0. So, we have proved that. So, there is one trivial exception here. The exception is that if f naught is equal to f 1, if f naught is equal to f 1, this quantity is going to be 0. So, this condition will not be satisfied, and of course, this relates to a trivial situation, because our testing problem itself is f naught against f 1. So, if they are the same, then there is no testing problem also. So, what we have proved that using theorem 3, we conclude that the sequential probability ratio test of Wald terminates with probability 1 under both H naught and H 1, of course, unless we have F naught and F 1 same densities. Therefore, this is a reasonable decision making procedure. Now, another important quantity is that how many observations on the average you will require. So, in the testing problem in the Neyman-Pearson theory, you have a concept of power. So, for a fixed size you calculate the most powerful test. Now, if I want to achieve a specific power, how many observations do I need? So, that can be calculated, because if I put alpha, then the constant is coming, and then using that thing we consider the probability of rejecting when it is false, that is the power of the test. We put that equal to is pre-specified number. Then how many n will be required, that can be calculated from there. Now, in the case of sequential procedure, you will have stopping time, that means when we will stop. Now, if we are able to take a decision on that and then we compare. So, of course, n is a random variable here. So, on the average, we call it average sample number, expectation of n. Then whether this is less or more, that we firstly we prove a theoretical result in this regard, and then I will give an example also. So, let expectation of z be finite and expectation of z under H 1 will also be finite. Then the approximate expressions they are given by expectation of n L naught 1 minus alpha naught plus L 1 alpha naught divided by expectation of z under H naught, and expectation 1 n, that is approximately L naught alpha 1 plus L 1 1 minus alpha 1 divided by expectation z. Let me call it 1 and 2. Let us prove these results now. Now, from the previous theorem, we have expectation n finite, and so from theorem 4, let me call this one as 5, the previous one was 4. So, from 3 we have expectation n finite. So, from theorem 4, expectation n can be written as expectation of S n divided by expectation of z. We proved the result that expectation of S n is equal to expectation of S n was proved to be expectation z into expectation n. So, I have just putting it in the denominator here. Now, let us consider under H naught and H 1 separately. So, let me take under H naught. Under H naught. So, expectation of S n, we write as expectation of S n given S n is less than or equal to L naught into probability of S n less than or equal to L naught. So, this is under H naught plus expectation of S n given S n is greater than or equal to L 1 into probability S n greater than or equal to L 1. Now, when H naught is accepted, then S n is less than or equal to L naught, and previous to that step it should have been between L naught and L 1. Okay. And just one step before, we have S n minus 1 greater than L naught. Then the difference between S n and S n minus 1 is that of a single observation. So, we can approximate expectation of S n given S n less than or equal to L naught by L naught. Similarly, we can approximate expectation of S n given S n greater than or equal to L 1 by L 1. So, we are putting the values of this as L naught and this as L 1, and this is the probability of accepting when it is true, and so that means it is 1 minus alpha naught, and this is the probability of rejecting when it is true, that is alpha naught. So, expectation of S n under H naught is approximately L naught 1 minus alpha naught plus L 1 into alpha naught. So, expectation of n under H naught is approximately L naught 1 minus alpha naught plus L 1 alpha naught divided by expectation of Z under H naught. In a similar way, you can see the other term also. Only the difference is that there the hypothesis will be H 1. So, similarly, we can consider say expectation of S n under H 1. So, this is expectation of 1 S n, and once again same thing we are writing S n less than or equal to L naught into P 1 S n less than or equal to L naught plus E 1 S n greater than or equal to L 1 into P 1 S n greater than or equal to L 1. Now, I will just use the previous argument that this S n we are approximating by L naught, and this is probability of accepting H naught when it is not true, that is it is equal to alpha 1 plus this is approximated by L 1, this is the probability of rejecting H naught when it is false. So, that is 1 minus alpha 1. So, we are getting that expectation of 1 n is approximately L naught alpha 1 plus L 1 minus alpha 1 divided by E 1 z. So, these are the approximate values of the average sample number, that is average number of observations that will be needed when the null hypothesis is true or the alternative hypothesis is true. So, this one is when the null hypothesis is true and then when the alternative hypothesis is true, and I will show by an example in the case of symmetric that it is turning out to be quite simple here. Now, we have also earlier written that we had approximated L naught and L 1 by L naught is approximately alpha 1 by 1 minus alpha naught, and L 1 is approximately 1 minus alpha 1 by alpha naught. So, if I take log, so L naught will be approximately log of alpha 1 by 1 minus alpha naught, and small L 1 is approximately log of 1 minus alpha 1 by alpha naught. So, on this if I apply theorem 5's approximation, because I can substitute this L naught and L 1 here, then from theorem 5 we have following approximations to average sample numbers. Okay. That is expectation of n, we are writing here greater than or equal to, actually we can use equal 1 minus alpha naught ln alpha 1 by 1 minus alpha naught plus alpha naught ln 1 minus alpha 1 by alpha naught, and divided by expectation of z under h naught, and E 1 n, that is greater than or equal to alpha 1 ln alpha 1 by 1 minus alpha naught plus 1 minus alpha 1 minus alpha 1 by alpha naught. I will demonstrate using one example given in the book of C.R. Rao, Linear Statistical Inference and its Applications. So, suppose we are considering observations from a normal population. Suppose we have IID observations from a normal distribution with parameters mu, and for convenience I am taking mean to be the variance to be unity, that means variance is known. Okay. So, we are considering the testing of hypothesis problem mu is equal to mu naught against mu is equal to mu 1, and we are assuming that this mu 1 is actually greater than mu naught. Now, for this situation the most powerful test exists by the Neyman-Pearson lemma. So, let me write down the form. Let us take, say, the probability of type 1 error is equal to 0.05 alpha 1, that is 0.05. Okay. The probability of type 1 error and type 2 error I am fixing both. Okay. The most powerful test of size alpha naught given by Neyman-Pearson lemma is reject h naught if root n x bar minus mu naught is greater than or equal to z alpha naught. Okay. Now, alpha 1 is the probability of accepting when h 1 is true. Now, when h 1 is true, we have actually root n x bar minus mu, this follows normal 0 1. So, when mu is equal to mu 1, we consider root n x bar minus mu 1, then this is less than z alpha naught, and then that means I have adjusted the term root n mu naught minus mu 1. This is the standard normal. So, this is equal to, so this implies that z alpha naught plus root n mu naught minus mu 1 is equal to minus z alpha 1. This means z alpha naught plus z alpha 1 is equal to root n mu 1 minus mu naught. let us take say mu 1 is equal to 1, mu naught is equal to say 0. So, and I have taken alpha naught and alpha 1 is equal to 0.05. So, z alpha naught and z alpha 1 that are approximately 1.65. Generally, we take 1.6499 kind of thing. So, just for convenience I am writing 1.65. If I do this, then from here n is equal to z alpha naught plus z alpha 1 divided by mu 1 minus mu naught square. So, that is equal to 3.3 square, that is approximately 10.89. So, n is approximately 11. That means, we need 11 observations for achieving a power of 0.95 when the type 1 error size is equal to 0.05. To achieve the power 0.95, I need 11 observations. Okay. Now, let us consider the sequential procedure in this case. Next, we consider the sequential probability ratio test here. So, we need to look at the lambda m term. Lambda m is the ratio of the joint density of the first m observations at 1 and 0, that is at h 1 and h 0 respectively. So, we write it here. So, f 1 m by f 0 m, that is equal to e to the power. So, 1 by root 2 pi to the power m, that will cancel out in the numerator and denominator. 1 by 2 sigma x I minus mu 1 square divided by 1 by root 2 pi to the power m e to the power minus 1 by 2 sigma x I minus mu naught square. So, these terms get cancelled out. This is equal to e to the power half sigma x I minus mu naught square minus sigma x I minus mu 1 square. We further simplify this, e to the power minus 1 by 2. Now, this sigma x I square term will get cancelled out, and this term will be there, mu naught. So, we just expand it here, minus twice mu naught m x bar plus 2 mu 1 m x bar minus this is minus here. So, I have taken plus here. So, there is a mistake here, this should be plus here. Then we get minus m mu naught square plus m mu 1 square. So, that is equal to, so if I take log of lambda m, that is going to be equal to m x bar mu 1 minus mu naught plus half m mu 1 square minus mu naught square. There was mu 1 minus mu naught here, and here it will become minus. So, this is a mistake here, minus here. So, this will be square. So, this is plus here and this will be minus here. So, this will be mu naught minus mu 1 square. Okay. Now, if I am taking, so we can actually write m mu 1 minus mu naught by 2, that is equal to twice x bar minus mu 1 minus plus mu naught. Okay. So, in SPRT, we have at mth stage accept h naught if x bar minus mu 1 plus mu naught by 2 is less than or equal to L naught divided by m times mu 1 minus mu naught. Reject h 1 h naught if x bar minus mu 1 plus mu naught by 2 is greater than or equal to L 1 divided by m times mu 1 minus mu naught. Otherwise, continue the sampling. That means, if x bar minus mu 1 plus mu naught by 2 lies between these two quantities, then we continue the sampling. Now, average sample number formula I have written here, that is given by this. So, here we need, I am fixing alpha naught and alpha 1 to be 0.05. So, these numbers can be evaluated, and we need further what is expectation of z. What was z? Z is again ratio, the log of the likelihood ratio. So, to determine the average sample number, we have to calculate expectation z under both h naught and h 1. Okay. What is z? Z is equal to e to the power minus half x minus mu 1 square divided by, so plus x minus mu naught square, and we have taken log here. So, this will go away, that is equal to half x square plus mu naught square minus 2 mu naught x minus x square minus mu 1 square minus, so plus 2 mu 1 x. This term gets cancelled out, you are getting equal to mu naught square minus mu 1 square plus twice mu 1 minus mu naught x. So, if I consider capital X here, expectation of z under h naught, that is mu naught square minus mu 1 square plus twice mu 1 minus mu naught into mu naught, that is equal to twice we will get twice mu 1 mu naught minus twice mu naught square. So, it will become minus mu naught minus mu 1 square by 2. And in a similar way, if I put mu 1 here, if I take mu 1 here, then this will become mu 1 minus mu naught square by 2. Okay. Now, for the problem that we are considering, we have mu 1 is equal to mu naught, mu 1 is equal to 1, mu naught is equal to 0, alpha naught is equal to 0.05, alpha 1 is also same. So, expectation of n. So, first of all, what will be expectation of z under h naught? This quantity will become equal to minus half, this will become plus half. So, that is 0.5, this is equal to 0.5, and we need to calculate the values given in this formula here. So, this will become 0.95 ln of 0.05 divided by 0.95, which we can easily calculate because it will be log of 19 here, that can be calculated, that is 2.49 something. We substitute all these values, we get the average sample number under h naught and h 1 both as 5.29. Note the difference here. In the previous case, we got 10.89. Now, I am getting 5.29. So, it is 50% reduction. So, there is 50% gain in the sample size. That means, with roughly half of the required sample size, we can achieve the same probability of type 1 error and the type 2 error and number of observation. Of course, this is a particular example. Then there are certain other empirical studies, and with some conditions on alpha naught and alpha 1, Chernoff in 1959, he has estimated that roughly there will be 4:1 comparison between the sample size in the fixed sample size case and in the sequential case. So, there is a gain, or you can say substantial gain, in using sequential procedures. Now, I will complete this lecture by giving one main result, which is called fundamental identity in a sequential analysis. Now, why it is called fundamental? Because it is useful in proving certain other rates and optimality results of the sequential probability tests. I will not get into too much of details. Let me give this result here. A useful lemma, that is lemma 2. Let u be a random variable which takes both positive and negative values with positive probability. The random, that is probability of u greater than 0 is greater than 0, and probability of u less than 0 is also greater than 0. And the random variable does not have 0 mean, and also suppose the moment generating function of u exists for some value of t, then there exists t naught which is non-zero, such that the moment generating function is equal to 1. And we can actually tell about the location also of this t naught. If expectation of u is less than 0, then t naught will be actually positive, and if expectation of u is greater than 0, then t naught will be less than 0. We do not prove this result here. I will give actually the application of this in the following important result. Let us call it lemma 3. So, as before, let x 1, x 2 and so on be a sequence of independent and identically distributed random variables with probability density function given by, say, f h x. So, just this h denotes that like we may have different hypothesis values h naught and h 1 etcetera. So, under h we are writing f h x. Okay. Consider any sequential procedure with a stopping rule and let n be the number of observations needed to achieve a decision. Let z is equal to z of x I be any measurable function, then probability that n is finite under H implies that expectation of e to the power t s n into phi t to the power minus n, that is equal to p h t n less than infinity. Now, what is this h t? So, this density under h t is calculated. This is given by e to the power t z x divided by phi t p and then f h x. This is also a probability density, because if you integrate, then in the numerator you will get phi t and then the denominator also this will be phi t. This is also a probability density. This phi t function is actually the phi t function is expectation of e to the power t x t z x. Phi t is the density function, the characteristic, the moment generating function of the random variable z here, and this S n is nothing but the z 1 plus z 2 plus z n. I will be skipping the proof of this actually. I have mentioned that this details can be found in the book of Rao in 1973, and I have already given the proofs of earlier theorem. So, this proof is not too much different. We actually consider this expression, we write down the expression in terms of the integral and then we just express it, we can see that it is actually equal to this probability. So, I am not getting into the proof, but using this we can actually have the following result, which is known as the fundamental identity of sequential analysis. What is the fundamental identity of sequential analysis? The fundamental identity is that if probability of modulus z greater than 0 is greater than 0, then expectation of e to the power t s n divided by phi t to the power n, this is actually equal to 1. This was actually probability of n less than infinity, that is, this is actually implying probability of n less than infinity is actually 1 under H. That means, the previous lemma holds. Okay. So, this is 1. So, these two are same and therefore, these two, this will become actually equal to 1 here. I will end this thing with another definition, that is called the operating characteristic of a sequential procedure. Operating characteristic of a sequential procedure. So, let theta belonging to omega be the parameter, and we are having h theta is equal to theta naught and h 1 is theta is equal to say theta 1, which is of course not equal to theta naught. So, pi theta, let me put pi theta prime, this is the probability of accepting h naught when the value of the parameter is theta prime. This is known as the operating characteristic function of the sequential procedure. Actually, you can see that if I consider pi theta naught is probability of accepting under theta naught, that is equal to 1 minus probability of rejecting h naught under theta naught, that is equal to 1 minus alpha naught. If I consider pi of theta 1, that is probability of accepting h naught when h is false, that is equal to alpha 1. So, using the fundamental identity of the sequential analysis, one can give the general expression for pi theta. So, suppose we have actually that probability n finite, this is true, okay, and let phi of tau be 1, then you apply this fundamental identity here. Then 1 is equal to expectation theta e to the power tau s n divided by phi tau to the power minus n, that is equal to probability of s n less than or equal to a naught under theta into expectation of e to the power tau s n given s n less than or equal to. So, we call it L naught and L 1 plus probability of s n greater than or equal to L 1 expectation e to the power tau s n s n greater than or equal to L 1. This is approximately pi theta e to the power L naught tau plus 1 minus pi theta e to the power L 1 tau. This implies pi theta is approximately equal to 1 minus e to the power tau a 1 divided by e to the power a naught tau, sorry, this is L 1 and L naught minus e to the power L 1 tau. So, one can actually find out the approximate OC function from the given expression. I will stop the discussion of the sequential procedures here. I have actually paid attention only to the sequential probability ratio test of Abraham Wald, and he basically gave it as an alternative procedure to the Neyman-Pearson lemma when we do not want to fix the number of observations in advance. And there are some advantages of this test, as you have seen that the average sample number is nearly half, at least in the example that I have carried out, and of course, some other studies are also there in this regard. I have in this course covered various theories of testing of hypothesis. Mainly I have taken two approaches, one is the Neyman-Pearson approach and another is the likelihood ratio approach, and these were the two prominent approaches used in the classical statistics. There are some decision theoretic approaches are also available, where we calculate the Bayesian tests or min max tests or admissible tests, etc. However, we have not taken into account these things in this particular course. The remaining part of this course I will spend on the confidence interval estimation. So, that is another topic of statistical inference. In the point estimation we give a value, whereas in a confidence interval interval we give a range, or you can say an interval where the parameter is expected to lie. So, this I will be covering in the next lectures.